Welcome back, students. So now in this part I'm gonna tell you about the electronic configuration, means how you will fill the electrons in orbitals. There are some rules, there are some proposed hypothetical rules plus significant rules about the stability of atom, which you will say in this part. So let's begin here. So next we'll move on to electronic configurations, which is very important because questions in your competition exam like IIT-JEE will definitely come from electronic configurations, because this is where the whole syllabus of structure of atom, it gets wind up. Okay, every concept get quantifies here. So that is the very important part of this chapter. So first of all, you should know the rules for filling the electrons in orbitals. There are various rules which you must be familiar with. The first is Aufbau principle. Aufbau means what? It means making up. So it states that electrons, they are added one by one to the various orbitals, means the orbitals which we are saying after the magnetic quantum number, right? So they are filled in the order of increasing energy, starting from the lowest. And the increasing energy trend is 1s, 2s, 2p, 3s, 3p, 4s, 4d, right, like this. So now you see, between 2s thing, what I was having p also. That's why there, when I was discussing the orbitals part, I said that between 2s also we'll be having some space. And where you can see here that 2p come, okay, and also 3s to 4s 3p comes. So, and 5s to 4s to 5s, you can see that 3d and 4p comes. So what are these, okay, and how this energy trend is decided, I'll tell you now in short. It is actually the n plus L rule, okay. I'll tell you. There is a rule which is known as, let me highlight it with a different color so that you will never forget this. N plus L rule means you have to count the N plus L and then you have to check that whether this is small or greater. This will decide your energy level. Also, by this diagram you can see, you can relate this thing like write 1s, 2s, 3s, 4s, 5s, 6s like this, then 2p, 3p like this, and just cross it diagonally. So 1s, then after 1s, you will come 2s, after 2s, you will come 2p, 3s, then 3p, 4s, okay, then 3d, 4p, 5s, right? Go in zigzag way, and you will get all your orbitals. Here again, it is written the same thing, N plus L rule. If in a neutral atom, the lower the value of N plus L, the lower is its energy. Okay. Now suppose if both have the same N plus L value, then you have to check for the N value. Okay, that because it will not be the case that N plus L can be same for two orbitals, right? So even if the sum is same, but N value may differ, so then you have to check the N value. Okay, if the N value is larger, that means it will be having more energy. In this way, okay. You see 1s, I have N is equal to 1, L is equal to 0, and N plus 1 is equal to 1, so it is the lowest energy, then 2s, then 2p, then 3s, you can see that. Okay, don't think that only S will have the lowest. You can see 2p and 3s. In 2p, I'll be having N is equal to 2, L is equal to 1. So total will be 3. And then 3s, I'll be having 3 plus 1, so 4. So that's why 2p has lower energy than 3s. And so my electron will go first in 2p. Okay? Then comes Pauli's exclusion principle. Again, very important principle. And this says that no two electrons in an atom can have the same set of all the 4 quantum numbers. That means every electron is unique in itself. every electron is designated by different quantum number. Suppose if even the n, l, m value are same for that, but s value will change, right? In other words, orbital can contain a maximum number of 2 electrons, and these 2 electrons must be of opposite spin. The same thing, like for example, if I draw here the say this orbital, suppose the value of n, one second, I will highlight it. The value of n for this is say 2, l is equal to 1, m is equal to say -1. Okay, so for this, even the s value will be either plus half or minus half, right? For this it is plus half, for this it is minus half, and so different set of orbitals we will say. Okay, so that's what I want to tell you, that no two electrons in an atom can have the same set of orbitals. So two electrons in an orbitals can be represented by how? It will be represented by this thing, either clockwise or anti-clockwise. Okay, here it's shown as a full arrow, but even it's not a full arrow. If I tell you, then it's like this thing. Okay, you can treat them as two shoes, okay, placed in opposite order, like this way. Okay, or something this and this way, opposite order. Okay. Then we have Hund's rule for maximum multiplicity. What this says, this says with the filling of electron in the equal energy levels, okay, that electron pairing in p, d and f orbital, okay, cannot reach until every orbital is singly occupied. Okay, it's not only about p, okay, even s will come here. S, P, D and F orbitals. Okay, any orbital. It's not about these names. Any orbitals, pairing will not take place until each will get it. Why it is written here P, D and F? Because in S already, if one electron comes, then the next electron will come in the same orbital, right? For example, for S I only have one orbital, like 1s I take or 2s I will take. So if my electron is entering this for the sake, then the next electron will also enter this same orbital, right? But for the p case, say suppose I have px, py, pz. For this case, if suppose my first electron comes here, then where my second electron will come? If I say have 2p4, okay, then where my second electron will come? My second electron will not come here. My second electron will first come here, then third will first come here, and then fourth will come here. So this is the rule that it will pair up only when every orbital is singly occupied. Okay? And this is due to the fact that electrons being identical in charge repel each other. Okay? When they are present in the same orbital. And this repulsion can be minimized how? If the two electrons move as apart as possible by occupying degenerate orbitals. Okay, this concept you will use in the chapter of chemical bonding. And all the electrons in degenerate set of orbitals will have the same spin. Okay. Again, orbital can be represented by a box and electron with its direction by arrow, that we have already discussed. Or any orbital can occupy only 2 electrons, okay, not more than that. And the number of electrons is given by in a subshell, that is 2 into the number of degenerate orbitals, and in a shell it is 2 into n square. That was the same case with the Bohr's model also, right? 2n square. And the maximum number of orbitals in a shell is given by n square, where n is my principal quantum number. This is the maximum number of orbitals in a shell. Orbitals, not electrons. Remember that. So if my orbitals is n square, that's why every orbital can accommodate 2 electrons, so that's why the number of electrons will become 2n square. Okay. Now what are the exceptional cases? The exceptional cases is of stability of half-filled and completely filled orbitals. How? Just check it out. Copper, it has 29 electrons and its expected configuration was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d9. But what happened? A shift of electron from low energy to 4s to high energy 3d. Means now what will be the case? It will be 1s2, I'll write it here. It will be 1s2, 2s2, 2p6, 3s2, 3p6, then 4s1 and 3d10. This one. Why? Because now this has become full filled d orbital. And this is more stable. Half filled and full filled orbitals are more stable because of two reasons. The first reason is your exchange energy. Okay. Exchange energy means what? The number of electrons which can be, permuted anywhere. Like in the mathematics, you deal with permutations and combinations, right? For example, these are my 3 p orbitals, px, py and pz, right? Now, if my electron can take place this space also, this space also and this space also, then obviously my permutations will increase, right? My permutations will increase. It can go anywhere and will be more stable anyway. But if the second case is if it can only occupy this space, then it can left with the two spaces in which my next orbital will occupy, right? So which will be less stable as compared to the previous case. So that is called the exchange energy. So in case of half filled and full filled, in case of half filled, say suppose this is half filled, okay, all my electrons are degenerate. They are like the same set of orbitals, right? Only the difference is px, py and pz in the direction here. And that is also hypothetical. But they are on the same degenerate orbitals, means I cannot even identify from here that this electron is from px only or py or pz. Means all these three electrons can be exchanged, right? And this increases their exchange energy, which lowers down their total energy and they become more stable here. So this is one of the major reasons for it. And so is the case of chromium also. This is the electronic configuration of copper, which I have just written there also. And so is the case with chromium as well. Okay, so this is the exceptional cases which you must know that why it happens, how it happens, why exchange energy matters a lot, right? Also, it has been seen that if say I have this much exchange energy, right? If say I have this, these are the half-filled orbitals. That means I have all orbitals with at least one electron there. So with that, my repulsion factor is reduced, right? For example, if I be entering the electron here only, okay, in case of 4s2, in case of 3d9, then there was a repulsion factor, okay, which will dominate over the stability factor. So these are the two factors which will decide the stability. And copper and chromium show this exceptional case. In chromium, if you will fill the electron, it will go to 3d5 4s1 instead of 4s2 3d6. Okay. So guys, in this part we saw how to fill electrons in orbitals like s orbital, p orbital, d orbital, f orbital, how many subshells they do have, what are the various rules like Aufbau principle, Pauli's exclusion rule, etc. Also, we saw that half-filled and full-filled orbitals, they are more stable as compared to others, which make a difference in filling up of electrons in the periodic table.
So this was all about the chapter of structure of atom, but the theory part is not sufficient, to get a confidence. So to get confidence, you must practice questions, and for that, in my next part, I'll be giving you JEE level questions, IIT-JEE level questions, so that while practicing those questions, your confidence will get boosted up. So just ready to boost up now, because in the next part, I will give you the JEE question. Stay tuned with me for that.